Now we got it. Okay. This topic is really up to chapter 10, molecular geometry. Molecular geometry is divided into three principal theories. Called the VSEPR theory, valence bond theory, and the molecular orbital. These theories primarily deal with predicting the three-dimensional structure of molecules. These can be predicting structures of ionics as well as molecular compounds, so the procedures will match as we go through. Now we'll have time to do the VSEPR and the valence bond, but we'll not have time to do the molecular orbital. And personally, in 42 years of teaching chemistry, the molecular orbital theory pops up very rarely, and when that happens, I will go review it, apply it, and then I won't see it again for another 15, 20 years and this kind of thing. But the valence bond and the VSEPR theory are very, very dominant in the next level of chemistry, so pay close attention. So here we go. The VSEPR theory means valence shell electron pair repulsion theory. So valence shell is a operative phrase or pair of words. Electron pair is the second operative word. Valence shell electron pairs are undergoing repulsion. Okay. When we deal with this, we're going to be talking about a central element and substrates. Central element, say AX2, is, say, the hypothetical molecule. Well, you could put this together in a generalization, whereas AX is bonded to A and again bonded to another X over here. And the bars, as you recall, are electron pairs. Now, these are bonded pairs. They have a minus or partial minus charge. Let's do it partial. They have a significant negative charge. And of course, likes repel likes. So what this means is, in the formation of a molecule in space, or the arrangement of a molecule in space, the substrate elements will assume a geometry in space that minimizes repulsion energy. and the formation of the 3D structure of the molecule, the substrate elements, those are your satellite elements, not your central element, will assume positions in space that minimize repulsion energy. If we take the structure here, the AX2 structure, it's like a coil spring, a fairly stiff coil spring, okay, and it has a line of symmetry through the middle of it. And so if you distorted that spring without exceeding the elastic modulus, of course, if you distorted the spring into this format or this format, you distorted it, twisted it down, or twisted it up, and then lay it back down on the table, both of them would spring back to this straight line orientation. Well, the molecule does essentially the same thing. If you have A with a strong negative charge here and here because of the bonds, there will be a strong repulsion. Just as A in this configuration would be a strong repulsion also. So both would have a tendency to arrange themselves in this configuration. And in this configuration, the repulsion energy is minimized. Right here. Now, what this leads to, and this is just the simple explanation of what we mean by electron pair. And of course, these are your result of valence electrons. These bonded pairs in there, bonded pairs are repelling each other. Non-bonded pairs can do a repulsion issue also, and we'll get to that in a few minutes. Now, what this leads to is what we call parent structures. 5 are in your book, a 6th one is mine, and I'll put all 6 of them down. And from those parent structures, we will get derived structures. So the parent structures parent geometries are linear, trigonoplanar. Yes, you have to learn these. After you work with them a while, they'll become pretty natural. Tetrahedral, trigonal, bipyramid, octahedral, and pentagonal bipyramid. Are your 6 published parent structures. These parent structures will apply both in the VSEPR theory, which we're working on right now, as well as in the valence bond theory, which we're going to get to in shortly. Linear structures, you will find them to be an AX2 type geometry. You'll have a central element and 2 substrates only. That means we talked about that as the examples up here. That's a linear structure because it would assume space, positions in space that minimize repulsion energy. Trigonoplanar has 3 substrates arranged around the central element, and we'll work through examples of those too. Tetrahedral, 4 elements around the central element, and it continues 5, 6, 7. AX5 for the pentagonal bipyramid. Now this would seem to violate the octet rule when we get to the AX5, but it does not violate the number of electrons per orbital structure, and we'll explain as we get there. Octahedral is an AX6 fundamental geometry, and AX7 is the fundamental geometry of pentagonal bipyramid. Now what I'm going to do is I'm going to go through calculating the various structures, and we'll be using a procedure like we did in the AVO Beck. And this doesn't have a name to it, but we will figure the valence numbers, the substrate numbers, not an octet number this time. It'll be valence would be the same way we calculated last time. Substrate, and then we'll calculate if it has free pair or non-free pair. Okay, so we begin with linear, of course, and let's start out with beryllium dichloride. Okay, now what you need is three things. You need the valence number, the substrate number, and the free pairs if it has any. So we're out of this, we're going to calculate the valence number, substrate number, not an octet this time, and number of non-bonded or free pairs of electrons. So there's really two phrases here: non-bonded electrons or free pair electrons. They're kind of the dots that were sitting above nitrogen, or the two dot pairs that were above and below oxygen, and so forth like that. Okay, when we calculate the valence number on this, where is beryllium? Hydrogen, helium, lithium, beryllium. That's in group 2. Okay, so we have a beryllium plus 2 chlorides, the same format. We'll have 1 times 2 plus 2 times 7, valence. So that's a 16. Substrate number is the attachments times 8, or the attachments times 2. Attachments times 8 is everything except hydrogen. If you see, say, a BeH2, then it would be 2 substrates times 2. But this is a chloride, and everything else is 2 times 8. So we have 2 chlorides, and so this is 2 times 8, or 16. Okay? Now to calculate the number of free pair or non-bonded pairs, it's your substrate minus valence over 2. Or no, excuse me, I take that back. Valence minus substrate. It switches. Valence minus substrate. So essentially this comes out 16 minus 16 over 2, or 0 over 2, which means 0 free pair. Okay? Now, in the designation of this structure, you have a central element, 2 substrates, which are your chlorides. A central element, 2 substrates. Listen to me carefully. If we had had a non-bonded pair, it would be listed out here on the end. Here is an AX2, and that would be a designation for free pair. Okay, and we'll get to that in a minute. Okay, but this has no free pair, which means that you have a central element, beryllium, and you have chlorine, just 2 of them. When you have 2 chlorines, it follows the format that or designation we talked about up here. Okay, it arranges itself in a linear fashion. So you can just put your bonded pairs here, and your chlorides and chlorides here, and that'll fill in like that. When beryllium fills up, there's only 4 electrons out there. Okay, it's in group 2. But chlorides do fill up with 3 non-bonded pairs. So you got 8 and then 4. Now, the next collection, let me stop for just a second. That going, expand. Okay. All right, we'll use here this example, boron trihydride on this one. What is its geometry? Well, as we're following along, I'm doing these in order. Now, you won't have this convenience when you get to test date, but I'm doing an AX2, then we'll do AX3 sets and AX4 sets and so forth like that, so you can see how they come together and so forth like that. Well, again, we need the valence number, the substrate number, and if there are free pairs. Okay, so the valence is a boron plus 3 hydrogens. Boron has a valence of 3, third group, plus hydrogen has a valence of 1, so we have a total of 6. Okay? Substrates. Only the satellite attachments are taken into account, and they're taken into account when they're full. Substrates are satellites and full. So we have 3 hydrogens, and that's 3 times 2, or 6. And then the valence minus substrates over 2 will give us the number of non-bonded pairs. Well, this one does not have any non-bonded pairs. We'll get in the next one, we'll. 0 free pairs. Okay, so it has 3 bonded pairs. How do you know it has 3 bonded pairs? You see that? It says 3. The number of attachments, bigger than Dallas, right there on the molecule is the number of bonded pairs. You don't have to calculate anything with that. Now, in a trigonal planar, this takes it to a trigonal planar. An AX3 doesn't have any non-bonded pairs out here, so you only have 3 substrates attached to a central element. So this is a parent that is called trigonal planar. Like that. And a trigonal planar will arrange itself in space with 120-degree bond angles. That's a theta B, like that. So this is a standard format for a trigonal planar. So for a BH3, it would look the same way. You would have hydrogen, 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 and you'd have 120-degree bond angles between the hydrogens all the way around, 360 total around. Now, our first non-bonded pair that shows up, okay, and that will be in SNCl2. Now, if you look at this right here, it would lead you to believe that, well, is it an AX2 molecule? Yes, if it does not have any non-bonded pairs, because the first non-bonded pair is going to go on the 10, SN, and it's going to influence the bonding of those 2 substrates right there. They repel, the non-bonded pair will repel just as much as the bonded pairs, electron pair repulsion. Okay, so again, let's calculate the valence number is 1 stannous, or 10, plus 2 chlorides, and a 10 molecule is down here, number 50, under group 4. So it's going to have a 4 valence. Even though it's way down buried way down in the chart, it is 1 times 4 plus 2 times 7. Okay? This is an 18. Okay, your substrate, you have 2 chlorides, and full on the chlorides is 8, so it's 2 chlorides. That's 2 times 8, or 16. So in the number of free pair, I'll bring this on up, is valence minus substrate over 2, which is 18 minus 16 over 2, which gives you 2 over 2 or 1 free pair. So in this molecule, you have 2 bonded pairs and 1 non-bonded pair associated with this central element. So when you draw this, you have 2 bonded pairs. They would have to go off in this 120 degree. Actually, it's not 120 degrees. It's not as much. And then your 2 electrons. This is referred to as a bent geometry. That just makes obvious sense. And it is a derivative of trigonal planar parent. And it's typically listed as an AX2E geometry. Test day, the SNCl2 has which of the following geometries? It'll have AX2, AX2E, AX2E2, or something of that nature. And you have to calculate it using this format. You'll notice on your handout there's also NO3 ion, anion. So the nitrate anion, the polyions can also be defined in terms of their three-dimensional geometry. So we will start with NO3 minus, and the calculations are the same. The exception, like in the ABO bet, was if it is a negative anion, you add an electron to the valence. If it's a cation, you subtract from the valence. So it's the same issue. So the valence number is based upon nitrogen, 3 substrates, plus 1 electron that gives it the extra charge. And so that is simply 5 plus 3 times 6 plus 1, 7, 6, 8. 24, okay. The substrate number, you do not, remember, you do not add or subtract electron numbers to the substrate. It is based only on a full shell. So it's 3 oxygens, which is 3 times 8. It's going to be 8 or 2, hydrogens are 2, is 24. So we have non-bonded pair or free pair is equal to valence minus substrate over 2, 24 minus 24 over 2, which is 0 over 2, or 0 non-bonded pair. So when we arrange this in, it's an ANO3. So we have 3 substrates, or 3 attachments, in a central element. So our arrangement is an AX3 parent and geometry. So a molecule can have both the parent structure and be the geometry of the molecule. And as an AX3, you recall, it's 120 degree bond angle in there. So you would build the picture of the NO3 in the same way. Now, if it's a polyion, you fill up, you can have more than 2 non-bonded pairs on a given element. You can draw it out like this. Okay, now one of the things here is that nitrogen doesn't have the octet, so one of the non-bonded pairs has to be slipped into a double bond right there to make sure you have an octet in here. So when you fill in all of the octets and then you look at your central element, well, it's got to have an octet too. Just remove one of the one of the free pairs and turn it into a double bond. And as long as it matches the octet rule, or duet rule for hydrogen is correct. I mean, there's no iffies about that. Now, it may not be the right molecule that you think it is, but it doesn't matter. As long as it conforms to that octet rule, everything's good. And what that means is that there has to be 8 electrons in each of these circles to conform to the octet rule. And the net charge is a minus like that. Okay. Let's see what else we got here. Sulfur dioxide is another one, SO2. Now this is a neutral compound. Valence is sulfur plus 2 oxygens. 6 plus 2 times 6 is 18. Substrate number is, we have 2 oxygens. 2 times 8 is, 2 6 is 12. 2 to 8 16, yeah. Okay, so your free pair is valence minus substrate over 2, 18 minus 16 over 2, and 2 over 2 leaves us with 1 free pair or non-bonded pairs. So we have 2 bonded pairs and 1 free pair that has to be taken into account in this. Now, listen carefully on this. All of the molecules we're working on right now are AX3s. Now, what does that mean? AX3s mean 3 electron pairs, not 3 substrates. The primary focal point of this is how are the electron pairs arranged around the central element. So you have 2 bonded pairs plus 1 free pair gives you 3 electron pairs total, which is in the is consistent with the AX3 parent. Like that. So that's basically what we're trying to work with right now. Even though it shows up looking like this, the electron pairs have to be set in that structure in an arrangement that meets the trigonal planar. So you will have a sulfur and 2 oxygens in here, but you're also going to have a non-bonded pair in there somewhere that will conform to the octet. And put a bond here and a bond here. And this is what I was showing you a minute ago. If we put this structure like this, that's an electron pair, and a pair, not everything is showing up in octet. Like if I went here, 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 and here. 2, 4, 6 is not an acceptable number of electrons for the sulfur. So if that's the case, I can just simply move 1 in here like that. And everybody is satisfied in it. This is what we call a resonance structure. This bond kind of floats back and forth, but for this purpose, you can leave it on one side. So we have now a bent geometry from a trigonal planar parent. So the geometry of this is an AX2E geometry from an AX3 parent. So to classify it in terms of it as a derivative. Okay? Everybody kind of seeing the pattern? It's just going to repeat itself over and over and over from here on. Stop me if you need to. I'm going to push right ahead. Now, the next parent structure is an AX4. And this deals with a number of molecules that, because you're getting more complex in the generalizations of structures. As a matter of fact, we're going to look at methane, CH4, ammonia, NH3, and water, H2O. Now, what do we need? We need to calculate valence, substrate, and free pair. And And so we're going to take this arrangement and we're going to go valence, make a table, substrates, and free pair. And then we'll get the geometry. And if you want to, the parent, we'll substitute the parent in here first. Well, geometry and then the parent, because and that somewhat generalized arrangement. Hinky. Okay, so we have to calculate each one of these or define each one as we go along. Your valence is a carbon plus 4 hydrogens, which equals 4 plus 4 times 1, and that's 8. Okay? Substrate is just 4 hydrogens, which is 4 times 2, which is an 8. Free pair is valence minus substrate over 2, 8 minus 8 over 2, which is 0 free pair. So the total number of electron pairs is all bonded pairs. So if you have 0 free pair and bonded pair, you have 4 bonded pairs. Just by looking at the molecule. Here, this one's got 3 bonded pairs. This one has 2 bonded pairs. That's where you get that. So the total of bonded pair electrons and free pair electrons gives you the total number of bonds for the parent. So this is a 4 bonded pair and 0 free pair. So the parent is an AX4 and the geometry is an AX4. So we will find that this is a tetrahedral. Geometry and tetrahedral parent. So both the parent and the geometry are the same in that molecule. You can draw it there. That is a regular tetrahedron. Let's come down, put the central element, and then bar, bar, bar. That's a carbon, believe it or not, and bar, hydrogen, like that. And if you need to see the tetrahedron a little clearer, that's a regular tetrahedron. Now, all of these will be tetrahedral based on tetrahedral parents. But one of the bars up here will be a non-bonded pair for nitrogen, for ammonia, and 2 of the bars will be non-bonded pairs for water. So, your valence is nitrogen plus 3 hydrogens, which is 5 plus 3 times 1 is 8. Your substrate is nitrogen plus 3 hydrogens, which is just 3 hydrogens. Sorry, I'm getting out of 3 hydrogens, which is 3 times 2 is 6. Now, the free pair would be valence minus substrate over 2, 8 minus 6 over 2, 2 over 2, or 1 free pair. You have 1 non-bonded pair, and you have 3 bonded pair, and your geometry is an AX3E. Now you have 4 electron pairs. You have 3 bonded electron pairs and 1 non-bonded. That's still from an AX4 parent. So everything starts with an AX4 tetrahedron. And here is your nitrogen in the middle. Right here, hydrogen, hydrogen, hydrogen. But one of the bars is a non-bonded pair. And you have 3 bonded pairs, like that. And the overall structure, again, is based upon tetrahedral type geometry, like that. Same way with water. You'll see the tetrahedron, but it'll be a bent. Now, this one is called a pyramidal geometry, okay, from a tetrahedral parent. Like that. Water does the same thing in terms of how it evolves into its geometry based on calculation. The valence is an oxygen plus 2 hydrogens, which is 6 plus 2 times 1, which equals 8 valence. The substrates are 2 hydrogens, which is 2 times 2, which is 4. And so free pair is valence minus substrate over 2, which is, of course, 8 minus 4 over 2, and gives me 2 free pair. So its geometry is an AX2E2. You have 2 bonded pair, 2 non-bonded pair, still 4 pair around that central element, which gives you an AX4 parent. See, all 3 are AX4 parents, but this is a bent geometry here, right there. And so we start with a tetrahedron like that. The oxygen is in the middle here, and then you have hydrogen and say hydrogen over here, but 2 bars are non-bonded pairs. And of course you can still see the tetrahedron as the parent structure in here, right there. So all of them are based upon the same parent structure as given in the structure. Ma'am?
What exactly does the E stand for?
Electron pairs.
Oh, okay.
Yes, ma'am. Like that's just up here. How many E's do we kind of right there? These are the E things right in here. How many of those are left over?
Yeah, I just wanted to.
Yes, ma'am. That's fine. That's fine. Ask. Okay. 1 polyion here. We did it a little while ago in AVO Beck. NH4 ammonia is the pyramidal, but NH4 would evolve to the tetrahedral geometry because we'd lose that non-bonded pair. The valence is nitrogen plus 4 hydrogens, which is equal to 5 plus 4 times 1. What do we do if we have a plus? Subtract 1, so minus 1 electron, and so that would give us a valence number of 8. Everybody still good on the why we subtract with the plus and add with the minus? Okay, the substrate number, straight away calculate the full shell. We have 4 substrates times 2. Well, I better put it in there, I'll confuse somebody. 4 times 2, that's 8. So you see we have a free pair calculation. Valence minus substrate over 2. Valence is 8. Substrate's 8 over 2, or 0 free pair. So no E's, so to speak, okay? No E's in here. So if you have 4 bonded pairs, 0 free pairs, then this is an AX4 geometry, and it's the same as the parent. So the ammonium ion has a tetrahedral geometry, and that's nitrogen in the middle. And if you wish to put a bracket around it, you can do so as such. Now, up to this point, everything conforms to the octet rule through a total attachment of no more than 8 electrons to the central element. But from here, we go into AX5s, AX6, and AX7. Well, that's obviously going to give us an overload on the central element. But because of geometry, the configuration only holds 2 electrons per orbital. And what happens is the valence shell undergoes what we call hybridization, and to accommodate geometry and the electrons. And this is what this means. We're talking about an AX6 trigonal bipyramid. That's BI. Okay. SF6, we'll start with that. Well, if you look at the sulfur molecule, it has a core structure of neon with a 3 S3 XYZ PXPYPZ, and this is full. That one is full, and you have 2 paramagnetics down there. These are diamagnetics like that. Well, if you want to hook a fluoride into here, you have to have 5 structures to add them into. Here we only have 1, 2, 3, 4. There are only 4 orbitals in that valence structure. So, for whatever nature reasons, this undergoes hybridization. Okay? And changes into, in the 3rd energy level, 1, 2, 3, 4, 5 orbitals. This happens when you get to the higher levels, and you'll see these have certain names. How about an SP3D, 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 SP3D. I hate to jump too far ahead, but it's like taking orbitals. Oh, there is a d orbital out here. It just doesn't have anything in it. And 1, 2, 3, 4, 5. Oh, I need another one, another D. What's happening is the electrons are jumping out here. Now this is an unhybridized, and then it goes into a hybridized. It's just simply the valence shell changes to accommodate the bonding. Only when it accommodates the bonding will it undergo. Now everybody's got 1 electron in it. So if fluoride comes in, which has 7 outer shell electrons, then these 2 can bond, and now you can have an electron pair that will make a bond. Okay, that's the technology of what's going on. The geometry, these bonds, 1, 2, 3, 4, 5, will assume a position in space, minimizes repulsion, and it looks like this. To draw this, draw a lazy triangle. Start with. Everybody draw a lazy triangle, just like that, where it's kind of off-center. That's all you got to do. Put a dot right in the middle, and then go straight up, and then 1 straight down, like that. And then draw lines going from the center to the points on the triangle. Those are the hybridized bonds. If you count them, there's 1, 2, 3, 4, 5. Each one of these will have a bonded pairs, and they will be connected to the fluorides, and you'll have 5 fluorides or 6 fluorides. I've got SF6 here, and I'm telling you one and generating another one. PCl5 is what I should have been working on. Well, this comes out octahedral. I'm sorry. You got 6. That's a pentagonal bipyramid, but an octahedron is like this. I had a brain that'd be dangerous. This is what we just drew. I described. Okay, there's your octahedron. This is an AX6, and this is an AX5, which is a pentagonal. No, it's a trigonal bipyramid. You get mixed up. All right, let me start this section over. I'll do PCl5 and you'll see how it works. PCl5, valence is phosphorus plus 5 chlorides, which is 5 plus 5 times 7. 7, 6, 7, 5, 35. Substrates. Yeah, you have 5 chlorides, which is 5 times 8 in here, which is also 40. And free pair is valence minus substrate over 2, which is 40 minus 40 over 2, which is 0 free pair. Of course, you have 5 bonded pairs from the formula. And so 5 bonded pair and 0 free pair give you a parent and geometry. AX5. Well, to accommodate those 5, the central element A undergoes hybridization. To 5 bond orbitals, what we call 5 hybrid orbitals. Each one with 1 electron in it. Some of them will have 2 later. But when you have this, draw your triangle, a vertical, another vertical, and these are your 5 hybrid bonds right here. Each one contains a pair of electrons, and your fluorides, or chlorides in this case, hook up here. And this is a bipyramid. Okay. Now, what if you had an SF4 structure right here? That could be a tetrahedron if you just went off the cuff, or it could be something else if you take into account the non-bonded pairs. Well, calculating the valence number, sulfur plus 4 fluorides, 6 plus 4 times 7, 34, right there. Then your substrate number, 4 fluorides, so that's 4 times 8 is equal to 32. Free pairs is 34 minus 32 over 2. That's 2 over 2, or 1 free pair. And from the formula, 4 bonded pair, like that. Now you have 5 total electron pairs. 5 total electron pairs is an AX5 parent. But it's an AX4E geometry. See, it's AX, this is the AX4, and then you have the E for the free pair. So it's still based upon the trigonal bipyramid. You draw your triangle, put your dot in the middle, and go straight up, and then straight down, and then put your bars to the corners. Now, there's a trick here that you've got to remember for test day. This is the first free pair that we're putting in. Okay, it goes in the plane of the triangle. first free pairs enter into plane of triangle for AX5 parents. So we have there, and then your 4 substrates will go in the other positions as shown here, 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 and here. Of course, you can see the still see the trigonal bipyramid from the structure. So this molecule is called, you kind of have to, let me see if I can get some perspective in it here, if I can get it in here. This is a bonded pair. The red is a bonded pair. This is a bonded pair, and this one is a bonded pair. Geometry is based, listen to only the bonded pairs, not the free pairs. The parent takes it all of it. But geometry is proportional or dependent only on bonded pairs. So if you look at this, you might see it like this. Another way to look at it, these are bonded pairs. This is referred to as a seesaw geometry. Seesaw is an AX4E geometry from an AX5 parent. The T-shape, yeah, CLF3 would be the next one. CLF3, chlorine trifluoride. Okay, valence is the chloride plus 3 fluorides. 7 plus 3 times 7, 28. Substrates, we got 3 fluorides. 3 times 8 is equal to 24. So free pair is equal to 28 minus 24 over 2. 4 over 2, or 2 free pair. And from the molecule itself, we have 3 bonded pairs. So the total is 5 electron pairs, which is an AX5 parent. But the geometry is an AX3E2, like that, based upon the trigonal bipyramid parent. And again, we draw our triangle, our lazy triangle, put a dot in the middle and go straight up, straight down, bar, bar, and a bar, like that. Now, the free pair enter into the triangle in the AX5 parent. So I'm going to put a pair there and a pair back there. Well, what you're left with is a central element attached to 3 substrates and what we call a T arrangement. You can look at it like this, and it has 2 non-bonded pairs. Some people will draw them like this. And it's a T-shaped geometry, and that's an AX3E2. And all of these are derivatives of the AX5 trigonal bipyramid. Okay, and the last one in this collection is the xenon difluoride, XEF2. Now, xenon is a noble gas, and the issue is with the noble gas is some people say, well, they're not reactive. Well, here's an example where it is reactive. So this is a molecule that is reacting as a reactive noble gas. So same calculations. Valence is 8 in this case, xenon plus 2 fluorides. So your valence number on a noble gas is 8, but the fluoride is 7. 2, 3, 4, 22, looks like. You have 2 substrates, 2 fluorides, so that's 2 times 8, that's 16. So free pair equals 22, valence minus substrate, 16 over 2, which is 6 over 2, or you have 3 free pair and 2 bonded pairs from the molecule. That's, just look at the molecule, there's your bonded pair. You total it out, 3 and 2 is 5 electron pairs, which simply means you have an AX5 parent that gives an AX2E3 geometry, and that one is linear because you will fill up all of the positions in the plane of the triangle. So if you draw your triangle, dot in the center, and go straight up and straight down, then your bonds, there's your central element, but you have 3 non-bonded pairs all in the plane of the triangle, and then your substrates above and below. So you'll see a linear geometry out of that. Okay? I know this is not the best way to spend your afternoon, but okay. The octahedron any questions on that? That's really, like I told you, you eventually get to where you just almost do these things in your head as you go along. You practice a few, and then you can look up some in a book. Any college book will have a geometry section and plenty of examples. Okay, the octahedral, which I inadvertently started with a while ago, is a AX6 octahedral parent, and we've got 3 examples in here. They got a couple of extras in there. We'll just do those 3: SF6, BRF5, and XEF4. And I want to do one more, IO4 minus. That's a polyion. That's always on the test. I just kind of give you. Okay, well, let's just substrates. Let's make a table. Substrates. Well, we've got 6 substrates, 5, 4, and 4. So those are bonded pairs. So the number of substrates attached are the bonded pairs. Okay, so the free pairs is valence number minus substrate number. Well, we've got sulfur plus 6 fluorides is, I'll come down here, 6 plus 6 times 7, 42, 3, 4, 5, 6, 7, 48. And this one has bromide plus 5 fluorides. Bromide's a 7 plus 5 times 7. 7 to 6 is 42. For that one, here you have xenon plus 4 fluorides. So that's 8 plus 4 times 7, excuse me. 28, let's see, 5, 7, 5, 35, 36. And this would be a IO4 plus 4 oxygens plus an electron because of the negative in here. That's an electron right there. That's 7 plus 4 times 6 plus 1. That gives us 24, 5, 6, 7, 8, 9, 30, 31, 32. Okay. Okay, so we've got to calculate our free pair, valence minus substrate. over 2, so that'd be, we got 6 substrates. Let's put free pair down here. So our valence is 48 minus 6 times 8 is 48 over 2. This one's 0 free pair. Here is 42. Valence minus 5 times 8 is 40 over 2. That's 1 free pair. And then here is valence 36 minus 4 times 8 is 32 over 2. That's 2 free pair. And this one has also, you can figure 4 times 8 is 32 minus 32, 2 free pair in there. So the geometries now are AX6, AX5 with 1 free pair, AX4 with 2 free pairs. 2 free pairs. So you can, the pattern is really repetitive to the point where it gets kind of boring. Now, putting the electrons in here is different than the trigonobipyramid. You have to put them above and below the plane as they enter when you first get to the free pair. Okay, here you draw a lazy triangle, dot in the middle, go straight up, straight down, and a bar goes from the center to each corner. So you got 4 in the middle, and 2 above, 1 above and below, that gives you 8. Or 6 bonds, excuse me. Okay, so this is, geometry is an AX6, so everything's bonded out. So our SF6 up here is we got a sulfur in the middle, and we got 1, 2, 3, 4, 5, 6. So this is an octahedron. Kind of hard to see maybe. And then you've got one coming down from the back side. But this is the parent and the molecule. The molecule and the parent. The parent and geometry are the same. That's what I'm trying to say. Now this one is drawn the same way, except when you put the first electron pairs in, they go above or below the plane. Above or below the triangle. So what you're left with in perspective is what we call a square pyramid geometry. And that's an AX5E, giving you 5 and 1. And then finally, you have the above and below, and this one will do the same thing. But your 2 free pair will leave you with what they call a square planar geometry. Square planar geometries. The only one that's left in this collection is the AX7, and I'm not going to do the derivatives. I'm just going to show you this is a pentagonal bipyramid. And you have to draw this with a pentagon. You have to start with a pentagon like that. Like we started with a triangle, and then we did a square, now a pentagon. A dot in the middle and go straight up. They have molecules that are actually structured in this geometry. and with non-bonded pairs on each point. Not make that so long. You have a central element and substrates that will arrange themselves to minimize repulsion energy. ClF7 is an example. So you have 7 fluorides attached to a central element, chlorine. Now, for a second.